increased capacity while new lines are built. Many utilities are already beginning from advanced grid solutions, but many utilities still feel additional research is needed. This webinar aims to increase understanding of advanced grid solutions and encourage sharing of information about them, including their challenges and benefits. System operators want to know how to include advanced grid solutions in system planning, as well as how to purchase, install, operate, and maintain advanced grid solutions. In today's webinar, after each 12-minute presentation, there will be about 10 minutes in which the audience may ask questions and share concerns with the presenters. In order to stay on schedule, I will ask people, if necessary, to continue their conversations after the webinar, and I'll introduce the next speaker at the allotted time. As the webinar is ending, you will receive a survey that asks if you are interested in any follow-on activities, including workshops that will go into greater detail about a given technology or whether you are interested in participating in case studies. So please look for that webinar on your monitor at the end of the webinar. Please fill it out and submit your survey responses. Next, I'd like to introduce Marcelino Madrigal, who is at the Inter-American Development Bank, and he is the chief of the Energy Division, and he'll share a few words.
Thank you so much, Melinda, and good morning, everyone. On behalf of the IDB and the RELAC initiative, welcome to this Advanced Grid Solutions Seminar. I would like to express my deep appreciation to the Global Power Sector Transformation Consortium, which is one of the partner agencies of the RELAC initiative, for putting this seminar together. As you all know, the RELAC initiative is globally the most ambitious renewable energy initiative in the world. 16 countries in Latin America intend to achieve 80% renewable energy share by 2030. Last year, they decided to actually increase that target because we were on track to meet the 70% goal. In addition, the initiative decided to also track the renewable energy contents in total energy supply, so it's even more ambitious. So, and of course, accelerating the decarbonization of the grid needs to invest much more. Latin America needs to triple its investment in the power sector, and no surprise, transmission is the segment that needs to grow the most. Why? Because we all know that more renewables require more transmission. Still is cost effective for a system to build more transmission, but building transmission is challenging. We at the IDB, as a financing institution, one of the largest share of our portfolio is for transmission and distribution, both inside the countries and outside the countries. Interconnecting countries helps a lot manage, variability and making our systems more resilient in Latin America, especially, with the impacts of climate change. We're seeing recently heat waves and the lack of hydropower. So transmission is not only a good tool to integrate renewables, but to make our systems more resilient to the new realities out there. So yes, we need to build transmission faster. It's not always easy. And while we build more, we need to look at new technologies on how to get the most out of the grids we already have. And this is the purpose of this seminar. We will hear from really top-notch experts, companies that are innovating in this space, power utilities, and think tanks all around the world that will tell us the new trends on new technologies to enhance how we use our existing grids. So with that, thank you, GPST. Thank you to all the RELAC members for your impetus on moving with decarbonization in the grid. Thank you all partner agencies, including NREL and many others that are here today. And with that, I'll just pass it to you, Melinda. Thank you very much.
Thank you, Marcelino. Sophie, I think you would like to give a few housekeeping remarks, right?
Yep, I'll make this quite brief so we can get into the content of today's webinar. As you may have noticed upon entering today's webinar, we are recording this session. The intention for that is to share the recording with all attendees and registrants following today's event. All participants will automatically be muted throughout this webinar. However, you're highly encouraged to use the chat feature to introduce yourself and add comments and inputs throughout each presentation. And if you have any questions for presenters, please use the Q&A function that can be found at the bottom of your toolbar. If you encounter any technical difficulties, please don't hesitate to chat myself, Sophie Schrader, and I'll do my best to assist you. You're also welcome to adjust your audio through audio settings or dial in. And closed captions are available and can be turned on for any language. And we also have live interpretation going from English to Spanish. So if you prefer to tune in to today's session in Spanish, please click the interpretation button in your toolbar and you can make that selection there. At the end of today's event, a survey will launch, and we really do review every single survey response to help improve future webinars. So please do consider providing us your feedback. And with that, back to you, Melinda, for speaker introductions.
Hey, great. Thank you, Sophie. Our first speaker is Xiao Li. He's with NewGrid, and he's going to talk about topology optimization. Xiao, please take it away.
Thank you, Melinda. Good morning, good afternoon, good evening, everyone. I'm Xiao Li, the Director of Product at NewGrid, and one of its co-founders. And today I'll give an overview of topology optimization along with 2 case studies. Next slide, please. So topology optimization is a software technology that can find and evaluate reliable grid reconfigurations to reroute power around congested facilities. And this can have a significant impact on mitigating congestion in the transmission network. Analogy that we like to use is a GPS app. So if you're driving and you hit traffic, you might pull out your favorite GPS app and then look for alternative routes to your destination. Well, similarly, the NewGrid software will find alternative configurations of the grid, identifying the selected few circuit breakers to switch among the millions of circuit breakers that exist on the system. So reconfigurations are implementable today. They open or close existing circuit breakers, and they require no new hardware. So in fact, it's not a new practice at all. Reconfigurations have been used since the beginning of the interconnected grid. Traditionally, they are identified by engineers based on their experience and expertise, but it is a time-consuming process, and that's why they're used on an ad hoc basis only. Even when they are used, they're not really typically referred to as topology optimization. So you may have heard of them being referred to as operating guides or remedial action plans. So, this has been around for a while, and you may wonder, if we have been using this all this time, what makes this an advanced technology? Well, because of how time-consuming it is to identify these reconfiguration solutions, they are severely underutilized today. Let me give you an example. Imagine you have a storm rolling through your system. You have transmission lines outage in several places, and your system is now under emergency conditions. Well, under that scenario, the last thing you want is to pull a shift engineer away from the desk and then look for solutions for 2 hours. Despite the fact that there may be really good solutions that can mitigate the reliability issues. So what our software provides is a way to find these solutions quickly and systematically. So we've tested our software on systems such as PJM, MISO, SPP, many European systems. These are some of the largest systems in the world, and we can find solutions in a range of 10 seconds to 2 minutes. So extremely quickly. And by the way, this is with a full set of contingency analysis. So moreover, we understand that the operator absolutely have to be in control. So we design our software to be an advisory tool rather than a control tool, so that a human is always in the loop. We really believe that this technology can be applied to a number of processes to greatly increase the flexibility and efficiency of the grid. So these different workflows, they differ in terms of how much effort is required to use the technology. So, for example, some workflows, you don't need to fully integrate the technology with the EMS system in order to use it. These are what we call the low-hanging fruits. And that's what I'll focus on in today's case studies. Next slide, please. So the first case study is a service that NewGrid provides to market participants in MISO. We started this service 3 years ago, whereby we monitor the grid for impactful congestion events that can impact the assets of our clients. And if we identify these events, we would then use our software to look for solutions to mitigate them. And then we will work with system operators and transmission operators to get them implemented. So, 3 years ago at onset, there was no official process to work with a system operator to request a reconfiguration solution. But I'm happy to report that has changed. As of last year, July, MISO has established an official process for market participants to request a reconfiguration. So the results that you see here, this is the work that we've done with Alliant Energy over the past 2.5 years. If you're not familiar with Alliant, they serve about 1 million customers in the states of Iowa and Wisconsin. And the results here is showing the results for IPL, which is their subsidiary in Iowa. So the results show that over that 2.5 years period, we've been able to save 51% of the congestion cost for IPL. That amounts to about $26.6 million. Out of the remaining 49% congestion cost, a further 31% could be further mitigated had the solution that we identified being implemented. So I mentioned that the process was only officially established in July. So a large period of this study, there was no official process. So we ran into situations where we would make a request to a transmission operator, and then they would decline to decline our request. And so what this 31% does not include is solutions that were declined due to a technical reason. For example, if there's a reliability issue due to the solution, that's not included in this 31%. So, overall, for a very large portfolio, we are able to reduce the congestion cost by 82% over this 2.5 period. So that's significant cost savings. And by the way, I want to mention that these are real, the 51% is real cost savings. It's not theoretical. And by that, I mean that we take into account the financial positions that Alliant has. So if they have FTRs or GFAs that is used to mitigate a congestion exposure, those are already accounted for in the numbers that you see. Next slide, please. So this slide, we're showing the same case study with the service, but I want to take a look at the results from the point of view of wind curtailment instead of cost savings. So here, there's a major 345 kV outage that lasted 3 weeks. So NewGrid was able to identify this ahead of time and know that it will have a major impact in the region. So we found a solution using our software, worked with MISO to implement the solution. And then afterwards, we did an ex post analysis to look at how much the wind curtailment would have changed had the solution not been implemented. And so what we found was that the curtailment was reduced by 86% just from the single solution. And that equates to about 37 gigawatt hours of energy. If you use some rough calculations to convert that to CO2 emissions, it's about 18,000 tons of CO2 that was avoided through the single action. Next slide, please. So the last case study, I want to show a software deployment. This is the system operator of New England. They are using the router, the new grid router software in their long-term outage coordination process. So the team that uses software is looking at planned outages in the weeks to months to years ahead timeframe. If they identify a set of outages that would lead to a reliability overload, they would then try to mitigate the reliability issue with a number of different types of actions. Among them will be reconfiguration. So the results here is showing over a span of 8 months, ISO New England studied 23 cases with our software, and engineers found promising solutions for 15 of them. So out of the 15, 93% is substation reconfigurations, and the remaining 7% is bus switch reconfigurations. And this is sort of typical of what we see. Substation reconfigurations will tend to give you more flexibility and more options to reroute power without further worsening another constraint. The chart that you see here is showing the flow on the most heavily loaded constraint in those cases. It is showing as a percent of the limit, both initially and then with the best solution that the software found. You see that in a lot of cases, the flow is reduced below the limit, and on average, there's a 28% reduction in the flow. So I hope this has given you a good overview of topology optimization and the benefits that it can provide. We believe that with a full deployment, meaning the software is integrated with the EMS, there'll be even more impact. But even for these low-hanging fruits, there's already a lot of benefits, so there's no reason not to use them today. Thank you. I'll be happy to take questions you may have.
Thank you so much, Xiao. That was a great description of topology optimization. We have a question from Juan Fajardo. Juan, would you like to speak your question? If not, I'm happy to speak it for you. I'll go ahead and read it. Does this software fit into the distribution system?
Great question. So it may or may not. So the benefit of the software is that when there's a meshed network, it could find powers to redirect, through different facilities. If the distribution system is more meshed, then it could be applied there. But if the distribution system is very much radial, as it tends to be the case sometimes, then there's not much that reconfiguring the grid can do. So it really depends on your system. But if it is meshed, it can work.
Okay, great. Sam Grant has a question. Sam, would you like to unmute your mic and state your question?
Good morning. I'm not sure if I'm audible, but I'll
Yes.
go ahead. Okay. Just wanted to ask, were there any data anomalies in that trend that you were sharing with us? And if so, how did that fit with the overall description and that you were talking about? I think there was a slide before this one.
Sorry.
So if you the previous slide, I think there was a bar chart that was shown.
Mm-hmm. you refer to a data
Yes,
anomaly?
long outages here.
Um,
So here, we're looking at the flow of most heavily loaded constraints, right? So I was asking, I mean, were there any data anomalies when you captured this data as all the way to the solution that we're, that's being proposed, 28% average reduction? And if so, how did that really fit in with the data analysis?
No, I don't think there were any data anomalies. So I don't know if you're referring to case 13, where seemingly there's no change in the flow. So sometimes there are a number of different constraints that is binding or overloaded. So here we're showing the most heavily loaded ones, but it could be that the solution reduced the flow on another constraint. It just doesn't show up on the number 13. I don't know if that answered your question.
Yep, it does. Thank you so much.
Okay. Thank you.
Okay, I have been asked to please read questions. So here is a question from Robert Lozano. And would this grid topology optimization solution be more appropriate on a project basis or to the grid operator, which sees all projects?
Yeah, great question. So I think from a software deployment point of view, this will make sense for system operators and transmission operators. They're overseeing a vast footprint, and they can really optimize the system that way. On a per project basis, where the technology could be applied is that there's an interconnection process for generators. And what we've seen is that sometimes, especially in the US recently, a lot of wind and solar plants cannot get interconnected because they're facing transmission issues that they then will need to upgrade the transmission system first before they can get connected. And there are solutions that topology optimization can provide to mitigate those transmission issues. So for example, where they interconnect, the substation could be configured in a way where if the critical contingency was to happen, then the generator gets isolated and then it wouldn't cause an issue. So there are applications for technology for projects.
Okay, thank you. Here's a question from Philippe Gonzalez to Chao. These case studies you mentioned, how often are grid reconfigurations taking place? Is it dynamically depending on the grid conditions, or are they defined beforehand for long periods, such as a day ahead or for the full 3 weeks during a wind curtailment reduction case or something like that?
Yeah, great question. So I mentioned low-hanging fruits. If you go back 2 more slides, but yeah, these reconfigurations that you see that these 2D solutions, they are very infrequently applied. I think maybe there are 20 solutions over a span of a year and a half. So we're looking at long-term outages in advance, and we study them, work with the system operators and transmission operators. The turnaround time could be weeks, and then we get them in place over a span of the entire duration of the outage. So it is not dynamically switching. That's where when you have a full deployment, with the software integrated with the EMS, you could have this more dynamic switching. But the results here are significant benefit, but with very, very simple solutions that sort of you just put it in place over a span of weeks. And it is, and these are robust solutions that will have to work under a number of different conditions.
Thank you, Chao. We have several more questions, but time for only one. I'm gonna hope that panelists will be willing to answer questions that we don't have time to address after the webinar. Here's a question from Barbara O'Neill at NREL. Would you be able to share cost per megawatt mile of transmission or some range of dollars for installation of equipment and for communications infrastructure?
Yeah, great question. So we do not require any hardware, new hardware, and that includes communication infrastructure. So circuit breakers are open today for planned outages and forced outages. So there's already, through the SCADA, there's already systems in place to operate the circuit breakers in that way. So it's really hard to place sort of a metric that's based on dollar per mile. Because it's a software technology that once installed, it applies to the entire system. So, if we're talking about a large system like MISO, once you install the software, it's really just the human resource that's needed to operate them. So, and it's a system-wide application. It's not focusing on a particular point in the transmission system. Working on a particular facility. So dollar per megawatt, dollar per mile metric will be very, very low. I guess if you multiply all the miles in the RTO and divide that by the cost of the software deployment, it's maybe $1. I don't know what. I don't think it's the right metric to use. But if you were to use that metric, it would be very, very low.
Thank you so much, Chao. We have a few other questions, but it's time for us to move to our next presentation, who's Joaquin Pirano of Smart Wires, and he's going to talk about advanced power flow control.
Thank you. There you go. Well, hi everyone. My name is Joaquin. I'm the regional manager for Smart Wires in the both Americas regions, or well, 3 Americas regions, North, Central, and South. I've been working in Smart Wires for the past 7 years, promoting the use of this type of solutions. So we're not going to talk. A lot of the focus, actually, my focus has been in Latin America. Only recently started to work more for the US. So I'm very happy to be here and presenting to my fellow Latin Americans. Yes, if we can go to next slide, I just get started. Okay, so first, I want to try to explain what the concept of advanced power flow control is. And just is the audio better now?
Yes.
Okay, appreciate that. What advanced power flow control is a solution that is capable of managing how the power flows on a line, right? Like the word says. I'm happy that we had the topology optimization case right before, because that helps illustrate the fact that when you have a transmission grid, you typically have more than one line that goes from the generation to the load. But these lines were built with different electrical parameters, different type of conductors, different lengths, different type of towers, which means that some of those lines are sometimes more attractive to electrons or the flow of electricity than others. So if you look at on the right side, we have this typical image of a transmission grid where there's 4 available paths. And as you many people here know, that we try to plan for n-1 contingencies. Sometimes what you see is that the contingency in one line starts to create overloads on some of the other parallel lines, right? But if you actually were to look at the loading of each line, you start to see that there's imbalance, right? The load, it's imbalanced, and that's precisely because of that physical characteristics that we were just talking. Some of the electrons, the majority of the electrons will try to get to the load using the path of least resistance. So power flow control is a piece of hardware that you can use to change that. And you do so by changing the reactance of the lines in real time. So you can either push or pull power. But what I mean by that is create the effect of an inductor or a capacitor. And at Smart Wires, we do this through power electronics, and that's why it's called advanced power flow control, because it uses voltage source converter technology, just like maybe you're familiar with other facts like STATCOM, right? It uses that type of technology, and it will, which injects a voltage in series with the line and will, and therefore create an effect of a reactance, right? That can be both either capacitive or inductive. And now the greatest innovation on this advanced power flow control devices is that they're modular, right? So we have these modules that you see to the left, where you have at least one module per phase that you need to install, and then how many modules you need depends on how much power you need to control. So how many ohms you need to solve the problems that you're trying to solve. So these modules, as opposed to traditional FACs, which have always been tailor-made, are much faster to produce. We're talking about maybe around a year from when we get the purchase order and when we can deliver. And they're all the same for whatever the voltage is that you're using it, because it works at line potential. It doesn't have a coupling transformer. And so therefore you just, as you can see there in the image, perhaps it's a bit small, but it goes installing on top of the insulators depending on the voltage class that you're going to install. But you can pick up those boxes and move them somewhere else in the future if the grid changes. So that's overall very interesting. I mean, working in this field for the past 10 years now, you see a lot of situations where, well, to give you an example, in Chile or in Brazil, where you have the backbone grid, right, the 500 kV or the high voltage lines that you build, but the transmission lines that are running in parallel, the older ones, the 138 kV, 115, 230 kV, are the limiting elements, right? So they act as bottlenecks for us to transfer the flow through the high voltage lines, right? And this type of solutions can solve those imbalances in a relatively quick fashion. So next slide, please. So we've been doing this at Smart Wires for quite a bit, since 2010 to be exact, with projects around the world, 25 plus utilities. And overall, a cumulative capacity, great capacity that we have unlocked is now coming to 3.5 gigawatts. And I put the word firm there because that's an important distinction, right? We're talking about hardware that goes on the grid. It is reliable hardware, and you're not subject to weather conditions or any sort of conditions, right? For whether you can use or not that available capacity that you're creating. Creating capacity obviously has a lot of benefits when it comes to the production costs and the ability to use lower cost resources, but it's also, optimizing the existing grid is much less expensive than building new, right? So we talk about $1.6 billion savings compared to traditional grid alternatives, either reconductoring lines or building new. Now, I'm not going to talk about all the cases around the world, but this slide that will be shared after just serves as an example of where we are. We had a very good presence in Europe, Australia, in Latin America. We've been very active, particularly in Colombia. I'm going to talk more about. And then, well, we're an American firm, so we have some good traction, obviously, in the U.S. With several deployments. So next slide, please. Just talking about the Colombia case as a good use case for us to have in mind. In Colombia, we have four different projects installed with 3 different utilities, transmission utilities. We have 2 projects with ESA in the northern part of the country, in the Atlantic Caribbean coast. One with Enlaza Grupo Energía Bogotá in the Bolivar area close to Cartagena, and one around Medellin with EPM. And the key facts that I want to highlight here is just the speed and what was the effect of this type of projects in the network. All of these were used to mitigate thermal overloads, either from that was impeding the new generation to connect to the grid, or to just improve grid reliability overall, right? And so started from the left with the ESA examples, we delivered about 47 of these modules that they were showing there, that are installed in 7 different circuits, all at 220 kV. Those projects took each of them about 18 months, from in-service to, from order to in-service. And they're creating about 500 megawatts of capacity for wind and solar to connect. Interestingly, one of these installations with ESA, it's going to be moved to another substation once the new transmission line that is being built in the Guajira area changes, right? So that's something that we see a lot, right? And we can offer in this this type of solutions, is that you install what you need now, but if in the future something else happens, new generation, new transmission line is built somewhere else, then you can pick the modules and take it somewhere else because they're reusable, right? In the case of Thermocandelaria, that's a gas plant, closed cycle. It used to be an open cycle that it was turned into a closed cycle, and created about 250 megawatts for a very small investment, and avoided building new lines or reconductoring new lines in an urban area, right? So sometimes that's something that is very important. Theoretically, it makes sense to build new lines or even change the conductors in some, but there's 2 main challenges that we see people have or utilities have. Is one, the permitting, especially when it has to do with building new infrastructure and acquire new right-of-ways in urban areas. And the second one is the outage. Sometimes you have a very critical line, and if you want to reconductor that line, you need to take it out of service, and that can be very hard to do. Sometimes making the project not feasible, right? So yeah, this is just a snapshot of some of the projects, and we have several others that I'm not talking here, particularly in Latin America. We've been very active working with the different transmission planning entities, like in Chile, or the system operator COES in Peru, the EPE in Brazil. All of them have moved forward with approving projects that are now either being tendered, and we're just continuing to expand our reach in Latin America with this type of quick solutions delivering value to our customers. I'll just stop there and maybe to just take questions. Don't have more materials.
Thank you so much, Joaquin. It's really interesting. Okay, we've got a question here from Pomudzo Mativa, and he is asking, have you ever used phase shifting transformer on any of your projects for power flow control? And what planning criteria do you use for the optimal location of these devices?
Yeah, those are great questions. So a phase shifting transformer is similar in effect to what we're proposing to do with these devices. The main differences lie on the way you do it, right? Phase shifting transformer, as the word says, it shifts the angle, the phase angle, and with that you can achieve the power flow control effect. Now, the problem that we've seen with phase shifting transformers is two. One, they have a very long lead time lately. We're talking about 5 to 7 years to get a hold of a phase shifting transformer. And secondly, they're mechanically tapped, right? So if you want to switch the parameters of how much power you want to control, you need to tap it. And that has led to many failures recently, especially in the US, where a lot of phase shifting transformers have failed because of the increased volume of renewables, right? These are devices that are meant to be fixed and not to be switching between different tabs. We use power flow control technology that's based on power electronics, and power electronics doesn't have that limitation on the how much you tap it, right? It's meant to be switching, and it's much faster to adapt to the system changes like those required by renewable energy injections. I'm sorry, the second part of the question is optimal location. So for optimal location, I mean, we run power system studies, trying to identify which lines, for the given constraints that you identified in certain lines, which are the lines that have more are more receptive to shifting reactance and how that affects the overloads that we're trying to solve. So if you have a line that is being overloaded, the first thing that you tried is, well, what happens if I increase impedance of that line? Does the power go into other lines in the system? Does that generate problems on other parts of the system? Then if the answer is no, we'll proceed to compare. We'll say, well, that's a viable solution. But what about if we also, do a capacitive injection on this other line that is underutilized, and so on. So we start comparing all that and try to minimize the number of modules that allows us to achieve the goal of solving the constraints.
Okay, great. Thank you. I have another question. These modules, well, let's see. It says these modules correct reactive power. What is the difference with StatCom?
Yeah, good question. So the StatCom is a shunt connected fax device that is used to control the voltage and reactive power. So it will address those voltage stability concerns, or just voltage going above or below the primary values, right? This is a series connected fax device. It uses the same technology as the StatCom, which is the voltage source converter, but instead of connected in shunt, you'll do it in series with the line, and that's what allows you to control the impedance of the line and not so much the reactive power.
Okay. I want to ask a question of Sophie, because I am seeing questions that are coming in Spanish, and I don't know if our interpreters are able to see these Spanish questions.
I can take care of those. I'll translate them live. So there's a question from Roberto saying, what's the additional space that you're required to install this devices? Well, depends on the number of modules that you require to install. Each module, it's slightly smaller than a 20-foot container that is used for transportation. So we make it so that it's containerized. And so we typically go ahead and look whether there's substation space available, and you can connect it there, or if not, end up doing some sort of substation expansion. Yeah, space is a constraint that we need to factor always when proposing this type of solutions. But compared to other fax devices or phase shifting transformer, is a much more compact solution. All right, next. Let me see if there is another one here in Spanish.
I don't see any other Spanish questions on your slides. Do you?
Yes, it was
No,
one
yeah,
from Peter.
okay.
Peter Santana, beginning.
Oh, yeah, it says, do you require changes in the grid to implement this solution? No, the answer is not necessarily. You would, you just try to manage differently the grid that you have. You just need the, obviously, the physical space to connect the devices into the grid. And I think that's it on the Spanish side.
I agree. Thank you for being helpful in that regard, Joaquin.
Absolutely.
There's a question for you. How often are smart valves being, quote, switched? Can they be controlled in real time, such as after a contingency?
Yes, they can be controlled after contingencies, as a remedial action scheme or post contingency, however you want to call it. The change is really fast, right? And you integrate it into EMS, or you can do a local control. It depends on the use case. Sometimes our customers only use it, on a fixed position for, say, the summer peaks. Or they will just leave the devices to automatically change in order to always maintain the system within their boundaries.
Okay, we've got two more questions. Here's one from Barbara O'Neill. I assume all your customers are system operators or transmission owners, but do you see any explicit cost pass-through to IPPs and generators in queue?
Yeah, that varies, I mean, per region and the regulatory scheme. Ultimately, the user of the equipment is the system operator or transmission owner, but we have had projects that are paid for, the IPPs or generators in the queue, who are looking to solve the bottlenecks that is not allowing them to connect, or reduce curtailment for what's worth. That's also sometimes a driver.
One last question. Does it look into generation cost changes as well as a result of power flow reconfiguration?
It will end up sort of like creating, reducing power production costs if used in the right way, right? Like, so that's something that the system operator will ultimately have visibility to, and when they run their dispatch, they will say, well, if I use the device and change the reactance this way, I can reduce power costs and tap onto these lower cost generation.
Okay, thank you. There are a few more questions that have been typed in, and if you don't mind answering those online, that would be great, because we need to move to the third presenter now. Thank you very much, Joaquin. Our third presenter is AJ Hall at AES Core, and he is going to talk to us about dynamic line rating.
Great, thanks, Melinda. Well, thanks for the good presentations on two other grid enhancing technologies, topology optimization and advanced power flow control or smart valves are just two new tools in our transmission toolbox that we can use to kind of address the challenge that Marcelina talked about at the start of integrating more renewable energy onto our existing grid and using it more efficiently. So today I'm going to talk about a project that's called a tool called dynamic line rating, and a project that AES worked with Line Vision last year to install 42 sensors across 5 lines in our Indiana and Ohio utilities. So what is DLR? DLR delivers transmission capacity on our existing lines. So you can see in the top left here, what are the factors that that drive the conductor heating equation. So transmission capacity is primarily limited by transmission conductors. It can, of course, be limited by other transmission equipment, such as transformers, switches, and those things. But the most expensive asset that limits and most time-consuming to build is a transmission line. And so existing rating schemes, such as static line ratings and ambient adjusted ratings, don't consider all of the factors in that top figure. Primarily, the wind is the most impactful driver of line capacity. You can see at the graph at the bottom on a cool, cloudy, and windy day, you may have, 2 to 3 times the capacity on a transmission line over the static rating, which is shown in the blue line there. However, when we have a very hot, sunny, and day with no wind, you can actually see kind of toward the right-hand side of the graph, there are times when our transmission lines may be operated at a level too high for what their true capacity is. So why pursue dynamic line ratings? Really, that's kind of the 3 use cases on the right. Is reducing congestion costs, and then improving reliability. So when, again, I think was talked about earlier, when the system is in an abnormal condition, using dynamic line ratings and taking advantage of that capacity to mitigate the effects of transmission outages. And then finally, it's enable economic development and more renewable energy to be connected to our communities. Next slide, please. All right, so how did we get started with DLR? Really, we started with 15 lines that were either congested, were related to economic development or renewable energy interconnections, or were being constrained due to construction outages for building other transmission infrastructure. We whittled those lines down to the 5 you see here, and these are the lines we've deployed DLR. And you can kind of see the use cases. We have connecting what we call step load or large customer loads, such as the data centers and manufacturing loads that we're seeing coming back to the Midwest here in the US. There's also a decent amount of reducing impact from construction outages. So, new transmission infrastructure sometimes takes months-long outages to connect and build, and that overloads other lines on the system. DLR is flexible enough to be deployed and mitigate the effects from those outages. And final item on this slide is you can really see we picked a diverse set of lines. So we have everything from 69 kV all the way up to 345 kV lines. Next slide, please. So how is the installation? I like to say there's no transmission physical infrastructure that you can install faster than DLR. It takes me sometimes longer to log into my computer and get everything up and running in the morning than it does takes to install one of these sensors. So typical sensor installation can be done you can see on the top right, from a 15-foot ladder. These sensors are mounted to existing poles or lattice towers well below the safety clearances of conductors and working at live voltage. So no outages are required to install the sensors. And really, frankly, even a bucket truck isn't needed, except for some cases. The sensors can go up in as little as 15 to 20 minutes once folks are on site, and can be done just with hand tools. They use a solar power module to power the equipment and use cellular communication. So there's no wiring in of power and utility comms. And then finally, they use a LiDAR sensor. You can kind of see that in the bottom left-hand corner toward the top of the picture there. There's a little LiDAR camera that looks up at the conductors, the 3-phase conductors in the span above it, right? And it's using that LiDAR position as well as a model of the span to calculate wind blowout, conductor sag, and pick out the solar radiation on the line. And these data inputs feed into a computational fluid dynamics model fed with third-party weather data to churn out a dynamic line rating. So essentially an hourly rating, as well as a forecast of 240 hours or 10 days of what the projected dynamic line rating is on the line, so that grid operators can use that information to operate the system. Next slide, please. All right, so what are some of the results we've seen from the deployment? So we actually now have about 9 months of data, but the information on the screen here is from the initial 6 months, October through March, so winter months of deployment. You can see on the left for 345 kV and larger lines, DLR is ready to scale right out of the box. These lines benefit from good wind conditions. Large transmission lines are higher up, have large right-of-ways, and also don't make as many heading changes, which require additional sensors to capture the wind direction. And you can see we achieved over the 6 months of deployment an average capacity increase of over 50%. To achieve something similar via reconductoring, we could have spent as much as $590,000 per mile, whereas DLR can achieve this with a fraction of that cost at $45,000 per mile. And importantly, we were able to do this and integrate this data into our operations in 9 months, versus it would be 2 years and take lengthy outages to achieve the same capacity on this line. On the right-hand side, we kind of highlight the situational awareness benefits of DLR, right? DLR, by putting these sensors in the field and understanding your transmission lines, you're going to realize or derive new insights about how to operate those lines. So it's kind of hard to see in the picture, but what you can see is a 69 kV line running through a very tight vegetation corridor. Currently, our static rating on the line inaccurately assumes a 2 meter per second wind speed for the entire line. However, we are not seeing that wind speed due to the tight vegetation in this corridor. So to increase the capacity of this line and maintain its existing rating, we could just fully reconductor the line, which would be the traditional solution at a cost of $1.63 million. However, now that we have dynamic line rating on the system, we actually only need to reconductor a half mile of that line, the part through the vegetation. So currently our system planners are looking at this project, but that would only cost about $400,000 and take less than a week outage to complete. So targeted reconductoring plus dynamic line ratings can reduce our grid upgrade costs, as well as ensure we're safely operating the lines and not using the assumptions that are made in static line ratings and ambient adjusted ratings. Next slide, please. So finally, I just want to close out and say, dynamic line ratings really is just another great tool in the grid enhancing technologies toolbox. We feel that integrating dynamic line ratings into operations has given our operators greater insights and to be able to safely and reliably operate the line. And we're looking to use this data derived in operations and how it can be used in transmission planning. As we think about how transmission planning is going to have to get more probabilistic, using more scenarios and less deterministic related on like summer peak loads, right? We're going to have to really understand an 8,760 hour profile of our system, and dynamic line rating has a place to operate in transmission planning. I'll take questions now.
Thank you so much, AJ. That's a fascinating talk. Okay, we've got a question here. What communications does the DLR device depend on? Satellite, PLC, Wi-Fi, etc.
Yeah, great question. So the sensor you can actually see kind of on the screen here, that in that silver box in the middle, right, it's relying on cellular communications. And so that is beaming back the real-time sag and line blowout information from the field. But importantly, that information is only used to train the ratings algorithm. If there was a loss of a sensor in the field, say a farmer came in and took out a sensor, it's not going to affect the delivery of the dynamic line rating because the algorithm has already been trained on the information from the field.
Okay. Philippe Gonzalez wants to know how many sensors are needed for DLR? Are sensors installed in every tower or only in a few of them?
Yeah, no, another great question. Yeah, so it kind of varies based on voltage. So that as you see here, this is a 345 kV line. We really had one sensor per every 6 kilometers approximately, but it sometimes can be less than that if there's a line heading change. As you can imagine, so wind direction can change based on when the line takes a turn. And since wind is the most important factor in calculating DLR, we have to put a sensor to capture the effect of wind for that line heading change.
Great. Oliver Probst is asking, in your comparisons with reconductoring solutions, are you considering only traditional ACSR conductors or also advanced conductors?
Yeah, no, that's a great question. So yeah, the cost information was actually based on the MISO cost estimating tool, and it's for ACSR reconductor. So yeah, absolutely. Advanced conductors like such as carbon core conductors, AES is also looking into those solutions, and that would be a different comparison.
Here's a good question. Henry Daniels Cock is asking, what are the technical barriers preventing widespread deployment?
Yeah, I mean, I think there's both technical and organizational and kind of culture barriers, right? So from the technical barriers, it's really moving from that pilot stage to deployment. So AES is in the process of doing that. We've done this first deployment across 5 lines, and now we're integrating into our energy management system, or EMS, that our transmission operators use. And then, as we get more of that information, it's really, the crawl, walk, run. We're ready to walk, and then when we're ready to run, it's selecting additional lines, and we're really seeing, again, on our 345 kV, great results. So we're really looking at further deployment on 345. And then on the people side, right, it's, transmission operators are being provided with new information, and there's a training piece, and there's understanding how to use that 240-hour forecast and what confidence interval of risk you want to take of where you want to operate your line based on that forecast.
Here's another question about the cost benefit analysis. This one from Barbara O'Neill at NREL. Do you compare DLR with static or ambient ratings when looking at your cost benefit analysis?
Yeah, absolutely. So the numbers in this presentation were compared to static because that's the existing rating schemes at both AS Ohio and AS Indiana. However, with FERC Order 881 taking place in the US and requiring utilities to move to ambient adjusted ratings at mid next year, we do also compare the ratings gains to ambient adjusted, and we're still seeing over 20% additional headroom gained above ambient, especially on our 345 kV. And notably, we are also seeing times when ambient adjusted ratings assumes that we have more capacity because we have less temperature. However, dynamic line ratings understands there's no wind giving us cooling. So where an operator may think he or she has headroom to operate with AAR, DLR is telling us, no, you don't, because we don't have the wind there. So I think importantly, as we move to AAR, we should do so with caution and really think about how DLR can augment that information from AAR on our critical lines.
Well, here's a question from me. Why are we being encouraged to use AAR and not just going straight to DLR? Are the wind sensors, the anemometers, expensive?
Yeah, so good question, Melinda. I think so. AAR, and it really depends on the implementation, can unlock additional capacity. It doesn't provide you just the wind speed, right? It's not informed by real sensors in the field. So you're still making assumptions based on third-party weather data. It's just, I mean, it's a cheaper implementation. It's a software-based and procedure-based solution, as many utilities employ AAR today. So there's a cost, of course, associated with DLR. I think how AES is looking at it is on our critical lines, and again, we have a large 345 kV infrastructure around the city of Indianapolis, and then also around the city of Dayton in Ohio. We're looking at DLR for those lines because of the large amount of power they move and how critical they are from an outage and transmission operations perspective.
I've got two questions here from Patrick Brown. I'm presuming it's our Patrick Brown from NREL. Is DLR still applicable and valuable for ACSS conductors or only for the more standard ACSR conductors?
I think it could be valuable for both. I really think stacking like the multiple tools in the toolbox that we're talking about today can happen. And so, yeah, I think if we have ACSS conductors, DLR, all of the technology would still apply, including calculating the heating of the line and then understanding the sag and blowout with the LiDAR sensor.
Patrick is also asking, what's the highest voltage at which you would consider applying DLR?
Yeah, I mean, AES only has 345 kV lines that we operate. And as I said earlier, I think DLR only gives you more headroom on higher voltage lines. There's more to go after, right? So I would definitely encourage system operators to look at larger 500 kV lines or 765 kV lines as your bang for your buck from a deployment standpoint is going to be the greatest if you think about just megawatt per megawatt miles of capacity that you're gaining.
Someone is asking, is this used already in operations and can you cite examples? Is this used already in economic dispatch on real grids?
Yeah, good question. So AES is still in the process of integrating the data from the DLR sensors into our operations, and we expect to do that early next year, kind of in conjunction, honestly, with the upgrades needed for AAR that many utilities are doing for the EMS system. This really just, once those upgrades are complete for AAR, this is really just an easy third-party plugin, is how we're seeing it. But there are other utilities in the U.S. and I know definitely internationally. From the U.S. side, Pennsylvania Power and Light, or PPL, I think actually won like an Edison Award, which is a major U.S. kind of award last year for their integration of DLR into operations in PJM, the Regional Transmission Organization. And I believe it is being used in their transmission dispatch.
Here's a great question from Asjadullah Qureshi. Are there any considerations for focusing target areas for installation of DLRs to minimize the cost and maximize the benefits? Like what areas are best for installation of this tool?
Yeah. No, that's a good question, and one that actually I think, so again, speaking from the U.S. side, that FERC is looking to address with a NOPR, or advanced notice of rulemaking, that they just announced a few weeks ago. One way of looking at where to apply dynamic line ratings is what lines are congested. So when you think from an operations standpoint, how can we solve congestion as that we talked about in the first presentation from New Grid? Those congested lines could greatly benefit from additional capacity. So doing that congestion study is a good way to understand what lines might benefit from DLR, and then taking that back and having your DLR provider understand, well, what is the wind potential and what is the historical weather performance on those lines? So what capacity could be gained? Of course, also factoring in substation constraints, other things other than the transmission line that limit you, right? Those have to be factored into your your project plan.
Thank you so much. AJ, you've got 5 or 6 more questions, but we have to move on to our next presenter. If you don't mind answering those questions online, that would be great.
Will do. Thanks.
Thank you. Our next speaker is Susanna Letta from Fluence, and Susanna's going to talk to us about energy storage as a grid enhancing technology. Susanna.
Thank you. Just for quick correction, it's Suzanne Letta. No problem at all. Nice to meet all of you. Thank you for including me. I'm the Vice President of Policy and Advocacy for the Americas region for Fluence. We're one of the world's leading battery storage product providers. And we are also, we're publicly traded, but we have 2 majority shareholders, Siemens and AES. So it's great to join one of my colleagues from AES on the line today. Next slide, please. So most people think about storage as, with respect to transmission, primarily as congestion relief, which is the on the bottom slide here, where you're moving power to different times of day to better integrate renewable energy. You're essentially using it to primarily shift energy, right, for grid operation. But actually, it can also be used for transmission operations specifically. And that's what I'm going to speak to today. And it can both increase the capacity of new lines, which is very helpful, but it can also minimize the need for further curtailment because you're increasing the capacity of new lines. So it's really about what can you do to maximize, just like all of my colleagues have talked about, another technology you can use to maximize the capacity of existing lines. Next slide, please. So this is just one example that we have utilized in a lot of applications, especially in Europe. We do have a couple of projects related to this in the Americas region. They're just not public yet. So I'm going to speak to a Europe example, but know that we're actively pursuing this technology, as are others, in the Americas region. And I'm just going to speak to one specific example, which I think is how it's being used most frequently, but there are other types of other ways you can use battery storage as well, like black start capability, for example. So in this case, the energy storage is being used to provide a curative grid operation to replace the N-1 requirement. So you start with sort of an initial condition, right, where you have 2 lines serving a high load area, where most of the renewable resources is on one end of the line. So in this case, it's primarily a wind energy resource on the top on the north end of the line. And that renewable resource is utilized to fully charge the what we refer to in this case as the grid booster, which is essentially the battery on the other end of the line. In the case of an outage, you have one of those lines coming offline, right? So in this case, you have congestion because you now only have one of those 2 parallel lines in operation. And that can be particularly problematic when you also have the wind capacity on the north end of the line also going down. And in that case, what you have the ability to do is actually use the grid booster to provide power back in the other direction or provide power to the load source. You can activate it so that to reduce the line congestion in that circumstance. And then once that grid booster is utilized, it's displaced by ramping up and down the conventional generation as needed. And then there's actually a slight typo here. It's not disconnected. It's always, of course, connected to the grid, but it's deactivated. And then it's recharged, and you can do it again and again. So you can take a look at this case study here online, but this is just a very simplistic way of thinking about how you can use a battery system simply for better utilization of the existing transmission grid. If you want to go to the next slide, please. This is a specific application that we utilize, where we utilize this technology in Germany. It was with TenneT, the TSO in Germany, the transmission service operator. It was 200 megawatt projects, so a total that are 2 hours of duration, so a total of 200 megawatt hours across 2 different strategically positioned sites in the north and in the south. A very high wind energy resource area in northern Germany, and it basically allowed better flow of the power from that high wind energy resource to other areas of the grid. It improved grid stability and increased utilization, and it also minimized congestion. And the other thing that's important is that it reduced the redispatch cost. And in Germany, those redispatch costs are very, very high. And as a result, it was a substantial cost savings to in that region. And it also, of course, reduced the need for further traditional grid expansion measures. If you go to the next slide, although this hasn't been deployed yet in a substantial way in New York, we do have an example of a market study in New York that looked at this type of technology in comparison to traditional solutions. And as you can see, it produced it at least theoretically in these cases with respect to the study, it produced some pretty substantial cost savings. And they did look at 3 different scenarios. In the first use case, the capital cost for the storage as transmission asset in the case of a 200 megawatt hour system is about 120 million. The wire solution would have been about 700 million. And that would have produced a local, either one would have produced a local area cost savings of about 9.9 million, and then congestion wide about 13.1 million. So you certainly want to have the least cost solution in this case, which would be the storage asset, to produce the maximum cost for both the local area and the congestion, the regional wide congestion costs. Similar cost savings with respect, actually more cost savings in terms of the local area and the congestion wide area costs in the second circumstance. So about 50 million in both, but even more, or actually maybe similar cost reductions in terms of storage as transition assets versus the wired solution in the second case. And that's for a 50 megawatt hour system combined with reactive power capability. And then a similar dynamic with the third scenario where you're still continuing to see cost savings. So those are just a few examples in New York where they're looking at deploying this technology. I decided to keep it very brief. So that is actually my last topical slide. Here's my contact information. Happy to take any questions.
Thank you so much, Suzanne. A great presentation. And let's see if we've got some questions. Well, while people are typing in their questions, can you talk about where, particularly in New York City, the study was? I mean, New York City is such an incredibly dense and complicated power system. Was this anywhere near Long Island or?
I'd have to look back at the research study. It was actually a statewide study, so it wasn't unique to New York City.
Okay.
And I'm happy to put the details more in the chat, but they did look at different areas of the state grid to determine where were the biggest areas of constraints, and looked at storage as transmission assets as solutions in different parts of the grid to try to determine, does this make cost sense? And certainly it does. It does.
Mhm. Are there particular, what are the circumstances or conditions where this is one of the perhaps first solutions someone should consider instead of maybe first trying another solution?
I think with respect to battery storage, the cost of the application is substantial, right?
Mhm.
And I think that's what's really notable about what each of the presenters is presenting on. So, some of our presenters are presenting software-related solutions that can be deployed in many, many areas of the grid that are sort of faster to deploy, but smaller in terms of their benefit, as in terms of each individual benefit. In the case of battery storage, the investment itself is large, but then the benefit is very large. So you want to deploy it where you really think you're going to get this maximum benefit vis-a-vis your traditional wire solutions. And that's why I think you want to be thinking about it in the case where you need to move a lot of power, right? So think about very big shifts in movement. I think utilization of wind energy would be a great example where you can have a big shift in power very quickly, and you need to be able to capture all of that on the other end of the line. So I think that's why the TNET example in Germany is very helpful. But one of the cases where we are deploying this in the Americas region that, again, I can't speak to publicly just yet, is in a region that's in an island. So it's they really are limited in terms of space, but they need a lot of power. And that would be another example, right, where you have pretty good access to both conventional and renewable resources. They want to be able to use more and more of those renewable resources, but they're just very physically constrained, right, in terms of available land. And so battery storage can be very helpful in that type of circumstance. So I think those are two examples where you'd want to use this technology, where you have a geographic constraint in particular, and also where you have to move a lot of power in a very short period of time.
Thank you. Okay, we've got a number of questions. Barbara O'Neill from NREL wants to know what's your size range for this non-wires alternative? She has 3 questions. What's your size range? Are you deploying in distribution grids or just transmission? And the third is, other than congestion, how do you measure benefit? So the first question, what's the size range?
So in our technology is what I would think of as very large scale battery storage technology. It's pretty much exclusively on the transmission grid. I think you can deploy it on the distribution grid, but you have to think about economies of scale. So in general, the best economies of scale are larger projects. In the Germany example, that was a 200 megawatt hour project. It doesn't have to be that large. Clearly, we have done the deployment. I think we have a system that's more like 7 megawatts. A couple dozen megawatt hours. So you can do it you can scale it to what you need, and that is one benefit of batteries, similar to these other technologies, is that they are modular. So you can really scale up and scale down based on what you need. But in general, it's a technology that's not as intended for the distribution infrastructure as much as it is for transmission infrastructure, just because of its scale. I'm sorry, can you remind me of the second questions, please?
Well, the second question was, are you deploying in distribution or transmission? I think you've answered that. Yep. The third question is, other than congestion, how do you measure benefit?
Well, you can measure benefit to, number one, your reduction of the curtailment of the renewable energy resource. So you're getting more out of that renewable energy resource. which I think is actually, I mean, it's not a dollars per dollar. It can be dollars per dollars, but it's also very beneficial from an emissions standpoint. You can also measure it based on the reliability of the grid, which is different than minimizing congestion, right? So avoiding congestion is one tool, but then you can also think about it as the overall benefit of grid reliability. And I think both things are very valuable.
Great. Here's a question from Felipe Gonzalez. In the solution that you presented, are the batteries used only for increased transmission capacities? Since they could be activated only after an N-1, they would be used only rarely.
It's a great question. So we think about it as we think about storage as transmission assets in two ways. One, what we refer to as SATOA, which is storage as a transmission only asset, and SATA, storage as a transmission asset. In the SATOA case, that is all the asset is being used for. And that generally is the case in that Germany example, which is why I wanted to mention it, because most of the time people think of these other values, right, that battery storage can provide to the grid. But it actually can't, if it's in those circumstances when it's used, even though it might seem rare, it's incredibly valuable. So you can use it only in that way. And sometimes, you know, in the case of the regulator, you may only want to use it in that way from an ease of cost recovery standpoint. However, it is an ideal circumstance if you can get your cost recovery mechanisms to account for these various benefits. You want to be able to use that asset in multiple ways. So it really depends on how the asset is being used and how your cost recovery systems work. But in the Germany case, that is the only case in which it's being used. It's just being used a lot.
Great. Okay, we have lots of questions. Afshin Matin says, the batteries are 1 or 2 hours duration in here. Is there a 4-hour solution now available?
Yes. So we at Fluence and our competitors as well provide many different a lot of duration variability. So we have a 1-hour solution, a 2-hour solution, a 4-hour solution. We can even do a 6 or 8+ hour solution. The technology is not the issue. It's just what makes the most sense from a cost effectiveness standpoint.
Okay. In Germany, how do they decide what specific service batteries are to deliver on an hourly basis? For instance, whether for congestion relief, energy arbitrage, or something else?
It depends on the need. So it's similar to how it would be here in the United States or in Latin America, right? So it depends on what the battery is being used for. In Germany, there's multiple types of applications. This is just the one application where it's only being used as a transmission asset, but it is also being used for, and I could have expanded on my slide deck, perhaps I should have, but it can also be used for capacity, as I mentioned at the very, very beginning, right, where you're using it to shift the power. It can be used for additional ancillary services. It can be used for black start. So there's actually a really wide range of applications. It can be used for grid forming. That would be another one. Lots of different applications that you can use with respect to batteries. It really just depends on what, number one, and actually this is probably most important, what the region's policies allow it to be used for and how the cost recovery rate structures work. And number two, what that grid system really needs most. And what is exciting to me personally is that there are so many different use cases, and there's so many ways in which you can deploy the technology. Where we're more behind is not on the technology, it's getting the policies in place to enable it.
Okay, great. Segue here, you mentioned grid forming batteries. And Ramana Buddha is asking, do Fluence batteries have grid forming capabilities? And if so, what's the technical readiness level? And if yes, where were these installed?
Yes, we do. It's called Ultra Stack. That's one of our product types. It's actually more than just grid forming. It's black start. It has a few different capabilities, but we actually structured this particular type of product for this particular type of use case. A lot of the secret sauce associated with that product is in the software, but there are some additional hardware components as well. So hopefully that answers your question.
We have time for one more question, and I hope that you'll be willing to write answers for a half dozen others. Someone wants to know, do you have any advice on the link between battery storage provided services and the location of the battery installation? For example, if the battery energy system has to provide frequency regulation, where should it be located on the grid?
It is not necessarily about where the battery is located on the grid in order to provide frequency regulation, for example. That is a consistent need in many parts of the United States, for example, where batteries have been deployed and are serving the grid, like ERCOT in Texas would be a great example of that. So it's less about where the battery is located and much more about what the interconnection policies allow for and what the transmission service operator values in terms of that resource. So that's where the policy comes in. It's less about the geographic location and more about structuring the market design to ensure that those resources can be used for those purposes.
Thank you so much, Suzanne. If you don't mind answering in writing questions that are in the box there, that would be great. Thank you. Our next speaker is Kevin Brem from the Rocky Mountain Institute, and he's going to talk to us about virtual power plants as grid enhancing technologies.
Good morning. I'm Kevin Brem, a manager with RMI, and buenos dias a toda la gente de America Latina. Thanks for joining. I am calling in from Colorado in the Rocky Mountains here, where RMI is based. If you're not familiar with RMI, while we started here in Colorado, we are now a global organization with 700 people all over the world. I'm going to speak a little bit about virtual power plants and leveraging DERs as they are aggregated into VPPs as non-wire solutions and integrated grid solutions. As I was listening to the remarks coming into this, a couple of reflections on what I'll be able to share and what I'll share. I think one reflection is the case studies I'll share are somewhat higher level. And I think that reflects a little bit our focus as RMI and VP3, the initiative that I'll speak of, which is looking at policy barriers, which is taking some of the think tank lens to think and research lens to thinking about these issues. I'd also be happy to share in the discussion some more specific and technical case studies. And I think the other element is, I think similar to battery storage, and that's a good segue to this, is VPPs have been primarily deployed, and we'll talk a little bit more about this, as a solution for managing peak demand rather than a T&D or non-wire solution. However, we're seeing an evolution and increased focus on that. So a little bit about the organization within RMI that I'm representing. I lead up our work on Virtual Power Plant Partnership. Virtual Power Plant Partnership was launched in 2023 to address key barriers and drive VPP market growth. I'll speak in the following slide about what I mean by VPPs. So we're housed within RMI and we're funded by industry leaders spanning the automotive, building, energy service, and software sectors. We are here to be a resource. We're creating resources. We're compiling them on our website, vp3.io. I encourage you to check it out. And also I've listed here some of our members. We appreciate their support, and they are the technical implementation partners that make these solutions possible. Next slide, please. So first, what is a virtual power plant? Our definition, and this is adopted from Department of Energy in their work on virtual power plant liftoff, a report they released last year. A virtual power plant is an aggregation of grid-integrated distributed energy resources that can balance electrical loads and provide utility-scale and utility-grade grid services. I think many of you who have been in the industry have heard VPPs perhaps in different terms over the years. There's an increased focus on VPPs and a lot of increased attention from utilities and regulators, especially over the past 2 years. But essentially, as we're talking about VPPs, we use a broad definition. So that's inclusive of a variety of devices that can toggle load, increase or decrease load. So that's inclusive of devices within the home, smart thermostats among them, plug loads inclusive. It's also inclusive of managed EV charging, battery storage. An important element that's part of the EV or the VPP story is devices like battery storage that don't just flex load within a building or behind a meter, but also can discharge power to the grid, and then also inclusive of what's been traditionally considered demand response and is continuing to evolve, become more grid dynamic and flexible, and that takes place often in the form of commercial and industrial loads. Next slide, please. VPPs are integrated solutions that provide multiple benefits, including T&D infrastructure relief. So on this slide, this is borrowed from the framework that was introduced by Department of Energy, where they identified 7 benefits of virtual power plants. We further have these listed from left to right based on survey we've done, non-comprehensive survey, but a survey of 8 utilities to understand when they think of virtual power plants, what are the benefits that they're most focused on? And I think these make sense, and I think it's a good framing for this conversation. So first, what stands out in the traditional bread and butter of VPPs has been resource adequacy, the ability above all to manage peak. Second, and an increased focus, is transmission and distribution infrastructure relief, and we'll talk more about that today. Followed by reliability and resilience, the ability to increase system resilience, including at critical facilities. Providing versatility and flexibility stands out as a key attribute of VPPs, as opposed to capital-intensive solutions. Affordability, the ability to offset investment needed in the grid and to ensure that the energy transition is able to be deployed cost-effectively. Community empowerment, enabling consumers and communities to have a different role in participating in the grid. Decarbonization and air pollution is final among them. Next slide, please. Transmission and distribution deferral is a key driver for VPP deployment and procurement. So I want to hear, I'm going to plug here a little bit of resource that we recently released, but I think helps substantiate this claim. So last month we put out a resource called the VPP Flipbook. It's a compilation of VPP case studies. There's a companion matrix that you can find that allows you to sort by 17 fields and to double click on some of the case studies and understand which of these might be most relevant to your specific scenario. So I went into that tool. I sorted by which of these VPPs are driven, at least in part, by transmission and distribution deferral needs. And 6 of the 15 profiled utility programs identified T&D infrastructure relief as a primary driver for their programs. So this is based on input from the utilities. I think we're increasingly seeing that as VPPs are being developed, deployed, and managed, T&D infrastructure relief is a consideration. Next slide, please. I'm going to share first a case study that's double clicking, and you saw this on the last slide in that red box. This is National Grid Connected Solutions. It's an example of an operating VPP in the United States. And I think the key element here is that, and I think we're seeing this in other jurisdictions, DERs, or VPPs being managed and dispatched initially for peak load management, and it's evolving towards DERs being used as a bridge to wires is the terminology they've used in National Grid service territory, non-wire solutions, or part of an integrated plan for expanding the distribution transmission systems. So a little background on the Connected Solutions virtual power plant. It was launched in 2016 as a pilot designed to manage peak load, and officially as a program launched in 2019. So I think just to sort of put this in context and for the conversation, VPPs have been discussed for a long time. This is a relatively early program when it comes to sort of the new generation of virtual power plants. So just to sort of anchor you a little bit on the timeline there and sort of the relative maturity of the solutions and the number of solutions that we're seeing out there. A key element of National Grid is that it's a multi-technology virtual power plant. So it involves residential thermostats, it involves residential batteries, as well as commercial and industrial demand response. Another key element is the structure of this program is that it's an open access virtual power plant. So that means it leverages third-party technology and service providers. Customer enrollment is performed largely by the original equipment manufacturers, say the smart thermostat, or third-party service providers, aggregators, or in some instances, the company that provides financial, that finances the solar plus battery system. And the program operator is Energy Hub, a VP3 member. The program is structured through performance-based payment primarily. So in the instance of battery storage, payment is $275 per kilowatt performed per summer. And we are, the program is growing participation and resource base. So in 2023, Massachusetts-wide participation was 227 megawatts from 96,000 customers. Okay, so I think the point there is that we have a bit of a track record in Massachusetts with National Grid. They've developed a program that works. It works for consumers. It works for third-party service operators. It works for the utility. They have a resource base in place. This resource base has been leveraged primarily to date for managing summer peaks. And now they're throughout the utility, they're recognizing the opportunity to increasingly leverage this resource base for emerging challenges that have to do with expanding and upgrading the distribution transmission system. So now we're talking about integrated distribution solutions. So National Grid is building on connected solutions to use distributed energy resources to address distribution congestion and reduce greenhouse gas emissions. National Grid can leverage the enrolled assets, like I was saying, and the capabilities they've developed to provide additional services. The Future Grid Plan, which was released in 2024, leverages VPPs alongside distribution infrastructure investment as part of the business plan for the utility for expanding and modernizing their distribution system. The plan aims to manage EV and heat pumps, driven load growth, leverages efficiency and DERs as non-wires alternatives. That's a term used by the utility in their documentation, and also to use customer batteries to avoid cost and enhance resiliency. So, I think to sort of name the maturity of this is the plan, this is the business plan. What we are seeing utilities increasingly do, and if they aren't, I would argue that they should be, as they're thinking of the challenge that many utilities are facing of how are we going to manage growing load? How are we going to manage growing pressure on the distribution system? Considering certainly there needs to be investment in traditional infrastructure, there needs to be investment in smart infrastructure, smart software solutions along the lines of what we've heard about today, but also to consider a utility would be remiss. It would not be cost effective if the utility weren't fully considering how can we leverage these distributed energy resources to provide this solution. Next slide, please. I'm going to provide a policy case study here, which I think drives home some of that same point, but it also points to the key importance of policy and regulation in enabling utilities to utilize VPPs as part of their solutions to distribution and transmission challenges. So I live in Colorado. Some of the motivating challenges here is there's been significant population and economic growth really over the past 2 decades or so. I think on the more micro level, there's increasing demand on a variety of circuits for building electrification, EVs, and distributed solar. The state had been seeing significant interconnection costs and delays for both new load as well as distributed generation. We are also in part of the arid West where wildfire-related risks are a significant concern. We're certainly looking to see what's happened in California and the major impacts that we've seen out there. And also within the state, there's been fires that have been pointed towards electrical equipment. So there's concern about that and the need to avoid those risks and modernize the equipment to avoid those as much as possible. I think one thing that we heard, I heard when we had our last convening where we bring together VP3 members was in Denver, and we heard from someone from the commission there about the expected $10 billion projected near-term T&D investment, which is a major challenge and is likely to drive rate pressure across the system. That's not something that anyone wants to see. So there's the recognition that, yes, there is the need for investment. There's a need for the right level of investment and the right type of investment. So given these motivating challenges, a broad group of stakeholders came together to develop a bill, now an act, that passed through the Colorado State Legislature. Again, I think the point here is VPPs are part of a comprehensive solution. So this bill took on distribution system planning, cost allocation, utility cost recovery, workforce training, interconnection processes and timelines. It also requires the utility to create performance-based compensation VPP program by February 2025. So that's a key element of the program and it's part of the integrated solution to dealing with the motivating challenges here. With that, those are my last two case studies. I wasn't monitoring my time. I can point to a couple other examples as well, or we could go to questions and answers.
Thank you, Kevin. That was a great presentation, and I really appreciate the Colorado focus. You're doing fine on time. We have a few questions here. One person is asking kind of a semantics question, I guess. VPP is not a technology, it's a concept, mainly market side. How would this fall under a grid enhancing technology? It's basically distribution energy, DERM management, microgrid, DR, and other resources aggregated.
So I think that's a fair, assertion. I think part of the reason that we find VPP to be a helpful concept in these conversations is I think even in your response, we recognize that it encompasses a broad set of both fundamental hardware as well as software solutions and approaches to this. So, I think when it comes to the utility, so that's sort of why we find the utility in discussing VPPs. Ultimately, yes, it's going to be a combination of a variety of hardwares. I think as we listed in that initial slide, whether it's load modifying resources, whether it's battery storage, and they're going to be brought together, like you said, through DERM, which is Distributed Energy Resource Management System. There's also a variety of emerging solutions that are more focused on grid edge aspects of the distribution management. But I think putting those together, we find VPP to be a helpful concept, both for utility planners, for utility operators, as well as for the regulators and policymakers who are involved in the sector.
Thanks, Kevin. Daniel Marin is asking, could you tell us about the main challenges in coordinating and controlling the various energy resources within a virtual power plant? And also, what technologies and strategies do you use to address these challenges and ensure that everything runs optimally?
Yeah, well, I think there's myriad challenges, and it's an important point. And I think one of the challenges, I think in a variety of contexts, certainly in the US context, is that when it comes to VPP operation or really grid operation, there's a variety of markets, there's a variety of approaches. So, one goal and objective is to increase standardization in VPP operations to allow both smooth operations within a jurisdiction, as well as to enable more scaled deployment of similar solutions across jurisdictions. Okay, that's relatively high level. So, so what are the specific issues that come up? with coordinating and controlling, I think there's a question of which sort of communications protocols are used. I think there's questions to which there's a lot of issues sometimes with both sharing information between aggregators and the grid operators, as well as between the actual hardware, and whether it's between the grid operator or the aggregator. I had a follow-up point there I wanted to make. What technologies and strategies do you use to address these challenges and ensure that everything runs optimally? So, I think one is there's a variety of approaches that utilities are making to these challenges, and they are diverse. So I think one opportunity is to, in the instance of National Grid, is they partnered with Energy Hub, which is very much focused on these solutions. And they've problem solved in a variety of jurisdictions how to ensure that they can integrate and reliably dispatch these resources, and have addressed some of the software and technical issues that might be involved in this. I'd take as another example Rocky Mountain Power, which is based in Utah. They have a program called WattSmart. And their approach has been, instead of doing that, their approach has been to start by defining which batteries meet the technical requirements to participate in their program and being really careful about and building from the ground up. So what technology and strategies do you use? Yeah, again, so I think there's the operational approach. Do you either make sure that you partner with an entity that is able to effectively sort of address these challenges and has experience with that? Do you really carefully test the technical requirements and the capabilities from the outset? And then I think from the other side, from a policy and sort of an industry level, is the attempt to continue to standardize our approaches to technical standards. And there's a wide range of technical standards, including communication standards. How do we do measurement and verification, et cetera? So it's a dense question, but I hope that at least stretched the surface.
Thanks, Kevin. Andrew Flagg wants to know, what are some of the actions you think energy regulators specifically need to create the enabling environment for VPPs? Yeah, so I'll point to two resources here, and I can go ahead and drop these, I think, in the meeting chat. One is a set of policy principles that RMI laid out. And the second is, I've mentioned it a couple times, but pointing to the work from Department of Energy on the VPP liftoff report. And I'll actually hone in on that because they have a shorter list of things to do and clear implications for policymakers. So I think the first part of their pathway to VPP liftoff is expanding DER adoption with equitable benefits. So putting in place policies that enable DERs to get out there. We need the asset base in place, and we need to ensure that they are deployed in a way that facilitate equitable benefits. Second is to simplify VPP enrollment. There's a lot of small policies that can be taken both from the utilities just to ensure that it's a streamlined process. Third, as I was talking about previously, was increasing standardization in VPP operations. So this can take place at a few levels, but ensuring that there's, I think some of the issues I spoke about before, integrating into utility planning and incentives. So that can be a complex topic often at the regulatory level, and thinking about performance-based rate making and other ways to ensure that utility incentives align with system incentives and have a role for DERs, and then integrating into wholesale markets. While FERC has done work through Order 2222 to ensure that, and this is in the US context, to ensure that VPPs can play a role in wholesale markets, there's a lot of work to be done to continue to ensure that they are smoothly deployed that they can be smoothly deployed and integrated into markets. Thank you, Kevin. There are a couple more questions. If you don't mind answering them in writing in the Q&A box, that would be great, because we've got to move on to our next presenter, who is Ibrahima Ndiaye. He's from GE Research. He will speak about advanced flexible transformers. And Ibrahima, I'm very sorry. I'm sure I mispronounced your last name.
That's okay. Thank you, Melinda. You have done much better than me. Thank you. Hi, everyone. Hopefully you can hear me. It's my pleasure to join the webinar and have the opportunity to share some technology improvement or development that GE Vernova mainly has been doing in the recent years with our core businesses in power transformer, mainly in the North America, which is product GE. My name is Ibrahim Njai, as Melinda was saying. I'm a senior principal engineer at GE Vernova Advanced Research. Probably everybody here know that GE has completed its split earlier in this April. Now we are 3 independent companies. There was GE Healthcare, there is a GE, or also known as GE Aerospace, and there is a GE Vernova, which is the energy segment now called GE Vernova, and I'm part of the Advanced Research Center of the GE Vernova. Can we go to next slide, please? So when we talk about advanced flexible power transformer, we have been developing a technology rightfully called so, because everybody knows how transformers are important for the grid. They are actually the grid enabler, allowing us to transmit power across a very, very long distances. That's really what made the grid that as we know it today. They are very, very reliable equipment, performing their work as expected, which is essentially transforming voltage from a higher side to a low side or vice versa. And we find them everywhere from generation step up to step down transformer. The transformer I wanted to talk about today are mainly transmission class transformer, which also are known as interconnection transformer. They are essentially auto transformer for several reasons, including they can be smaller at the same MVA rating compared to conventional transformer to a 3-winding. And that makes them easy to transport, especially up to certain power range to different locations, because as we know, most of our line, they connect sometime in remote area that are not easy to access. So auto transformer give that opportunity to reduce the size and the footprint. Because they are everywhere, so they are really the knob at the grid. So what we call really flexible transformer is an interconnection transformer that has an adjustable leakage impedance. Transformer has been here, as I mentioned, for close to a century now. They have never been known as having the capability to vary their impedance. We came up with that breakthrough, and this figure that I have here explain you how we went through. Technically, if you can imagine a transformer being in series with reactors, you can easily then see the reactors maybe being part of the core of the transformer. Technically, if you have the reactor and you put inside of the transformer, you can still be having different value of leakage impedance if you tap that additional reactors. But as soon as you do that in the transformer, you effectively change one of its most important parameters, which is the turn ratio or the voltage ratio. To avoid to change the voltage ratio of the transformer, if you add the same number of turns that you were figuring out as the reactors in the opposite direction to cancel the exact magnetic flux that you added, the number of ampere turns as we know, then you just negate that additional reactors in the winding ratio. But because the coupling can never be perfect, then you suddenly have access to additional leakage impedance. If you have tapped that leakage impedance at different position, then you just have yourself a variable leakage impedance. If you complete that design with a tap changer, as we know today, for instance, we are using for voltage, then suddenly you have a transformer with a variable leakage impedance. That's really how we went through that technology. And obviously, a tap changer, as we know today, for on-load tap changer for voltage, they can be controlled remotely. So if you do the same thing for the leakage impedance, then we suddenly can control the leakage impedance of a transformer remotely. And obviously, this technology also, we can build it with different voltage ratio. At the end of the presentation, I can explain a little bit why, but it is just to make them a more comprehensive technology. But really back to the application of having a leakage impedance, if we go to the next slide, you can see that there is a different way today to do power flow control. before I cover the active transmission, if you think about today, the network as we know, the active power really flow through the impedance, relative impedance of the different lines. Very rarely that we actually have lines with active power control, and some of my my colleagues with the previous presentation cover some of those aspects. But as we know today, the power transmission network is essentially a passive system. Pretty much no line is really being controlled. But there are technology that allow us to do really active control. One of them that are well known are phase shifter. And if you look at the equation of power transfer capability, there are really three parameters that we can use to actively control power. It's either we change the voltage at the sending end or at the receiving end, or we change the phase angle between the two buses, or we change the impedance. All of those technology, except maybe HVDC, high voltage DC current, are really acting to those parameters. And if you think about it, they have different, if you will, cost aspect and different challenges for each of them. If you think about having the voltage to change from one end to another, most of the time the constraints are also obviously the voltage class. But here we are not necessarily thinking of changing the voltage significantly. But as soon as you do that, it needs to go along with the rating of the equipment. And the way to change actively voltage today is either we boost it to one end by adding shunt compensation. The other end, obviously, is to do the same by adding things that we call shunt reactors as well. But the most common really for active power control, as we have heard, are phase shifter or series compensation. Obviously, series compensation are also well known for very long line. They have never been proven to be really cost effective for shorter lines. All those technology, however, what they do have in common is they all add additional infrastructure, meaning they all need to be built in either separate substation or extended substation. They also do have some reliability challenges. They need to be wired remotely controlled. What a flexible transformer uniquely offers is it is one single equipment that combines the transformer functionality and series compensation, or if you will, a compensation platform on the line. And the benefit of that is obviously cost and is obviously ease of integration to the actual network. Again, referring back to my first statement, transformers are what enable the grid. So obviously we find them everywhere. So once we instrument transformer or give them the capability to be able to do active impedance change, hopefully we can more effectively be able to control the power flow in the grid. If we go to next slide, please. This is the picture of the world's first flexible power transformer that has been developed and designed by Prolec GE and then the Advanced Research Center where I belong to. This is showing 60 MVA on class or natural cooling rating auto transformer with a variable impedance from 4% to 9%. It has been installed and energized in October 2021. So it has been in operation since then with really no sign of failure. It has been installed at a cooperative energy substation in Columbia, Mississippi in the US. But we do have the capability to build the technology up to 750 MVA, three-phase, up to 345 kV, and the impedance range that I'm actually showing. Obviously, we can do higher than this rating. The reason that we think this will be the most optimal, at least if you take the US grid, 230 kV has been the backbone of the grid, which means that's really where most of the interconnection happen. Now through electrification and decarbonization, the backbone is growing toward 345 kV. So that's probably where most of the interconnection will happen within the next 2 decades while we build out the next generation of grid. But if you think about it, in terms of footprint, as you can see, there is really nothing that suggests a different type of transformer compared to existing. The only thing that might draw your attention is the protrusion of the impedance step changer which is located really under the conservator, so it doesn't necessarily add any footprint. And we are showing here the impedance tap changer control, which we can wire from the substation control room, or obviously remotely from SCADA. Other than that, it has all the features and the same component, the same hardware, the same material as used today in conventional transformer. It doesn't involve any power electronics. So obviously, the reliability was very important to us because of how critical transformers are. So we are using only known and compatible material to design and manufacture this flexible transformer. If you go to the next slide, please, we have a user case, how it did operate to the grid. So the first graph is showing in a purple line the active power. The red one is showing the active power. The second graph at both sides, on the right side and the left side, are showing the impedance tap changer in the light blue. And the dark blue is showing the on-load tap changer, as known as is in many transmission car substations. We were also trying to capture through our remote monitoring system the solid gas, because we wanted to prove that the tap changer operation doesn't suggest any sign of early failure or gassing inside the transformer. And obviously, as I mentioned, we were also looking at the voltage ratio, which is, again, one of the most important parameters of a transformer. And as you can see, when we were starting to change the tap changer of the transformer from the low value to the high value using staircase, you can see compared to the right side figure that we were aggressively dropping the power through the line, through the transformer, as you can see. We are not showing here the natural load flow on a daily basis through this power transformer, but you can sense how aggressively the voltage was dropping. And in the other figure on the right side, when we were going in the opposite direction, dropping the impedance tap changer from the highest value to the lowest value, you can see, although the power remained maintained, but it suggests more power was coming through the transformer, because again, the natural flow through this transformer is power will drop around midday and go back to a peak around 5 p.m. time frame. So that's what we typically call the duck curve. Importantly so, you can also notice at the bottom curve that the voltage ratio of the transformer did not change at all. And this was more like a sort of a radial, slightly radial system. So there was no active power at the low, at the secondary side of there was no active generation at the secondary side of the transformer. There was only active generation at the primary side. So we were not trying to do anything to maintain that voltage ratio. So this was giving really the confidence that the transformer, flexible transformer, as a powerful controller, is working and operating as expected. The other slides, please, has another user case showing the same transformer when it is operating in parallel with a similarly sized transformer. You can see at the point of parallelizing the two transformers, the original flexible transformer was taking the full power. As soon as the second transformer is put in parallel, they were sharing the load. At the beginning, the load was not perfectly shared, but when we match the impedance, you can see the two transformers are exactly now sharing the amount of load. And obviously, when you increase the impedance value at the flexible transformer, that transformer is taking less power, which is the purple curve, compared to the other transformer, which doesn't have a capability to change its impedance. And then rightfully so, when we reach the maximum impedance and start dropping again, the flexible transformer is taking more of that power. So some also a concern that we wanted to remove or to retrieve from this deployment was some utility was asking about circulating current. And as you can see, the bottom curve here in the dark blue is showing that there is pretty much no circulating current except when the impedance is transitioning. And it's a relatively small number. That's the actually only time that you can really sense that there is an active change of the leakage impedance. Other than that, there was no adverse impact on the grid side. There was no tripping, no voltage dip whatsoever. So this proves again that flexible transformer can be operating fairly safely to the grid to manage power flow and to be relieving scenarios such as congestion, as many have taught, or grid reconfiguration during contingency. And the next slide is my last, just to sum up. So the design and development of flexible power transformer can comply to existing standard. In the North America, we apply mainly IEEE, so it can be designed to also comply to IEC standards. As I just mentioned, there is no adverse impact on the grid operation. It can be operationalized through EMS system and controlled remotely through SCADA. It effectively allowed to control power flow, therefore to relieve congestion, and then to be dynamically helping the grid to absorb more intermittent renewable resources, including avoiding curtailment where it is needed. It is customizable because it can be designed as a neutral transformer, as a more conventional transformer. It can be designed as a single-phase transformer or as a three-phase transformer. And the flexibility in the impedance also allows other benefit, including short circuit management, especially during emergency, where it can help transformer or line to be reconnected at the highest impedance, minimizing the inrush current, the disturbances, and then control to a more conventional impedance level once the grid is stabilized. Hopefully, I give you enough overview. I'm more than happy to answer additional question. I did not add my contact, but my email address is my last name, jai@ge.com. So please feel free to reach out beyond this webinar if you have follow-up questions.
Thank you so much, Ibrahima. Philippe Gonzalez has a question. He wants to, he says, I understand the advanced transformer provides a similar service to PSTs. What are the advantages of this solution with respect to a PST or fax device?
Right. That's a very good question. So one of the PST in general is usually also an additional infrastructure, as I mentioned, use additional real estate. It has been also reported that, you know, because of the different tap position, I don't want to say reliability problem, but they require way more maintenance, obviously, than transformer. This technology is essentially the transformer itself without any additional infrastructure acting on a power flow control. So one of the key benefits that we think here is, as far as real estate or replacement, this might end up being more cost effective. Although PST might have more power, maybe to cover a much wider range of power flow control, but we think in terms of penetrating at a high extent to the grid, the flexible transformer is bringing that differentiation of lowering costs and being able to go to much more, if you will, interconnection substation in the network. And obviously also PST act more on the phase angle, while the flexible transformer act on the impedance of the line. So the PST will have no contribution as far as short circuit management. The flexible transformer can indeed has impact on short circuit management, so give an additional opportunity to cope with grid when they are going from maybe weak to strong, or when they're going from strong to weak as well. Hope that answered the question.
What I'm wondering, Ibrahima, are those exactly the considerations that were used in Columbia, Mississippi, when they were the first flexible transformer installed? Why did they choose that solution, you know, instead of PST or fax?
Yes, PST was not cost effective for the application. They were using a 165 kV system, as it is shown here. Their line is not mostly congestion. They were more interested in having a solution for grid strength evolution for next generation of grid. And that's where the flexible transformer was the fit. But the benefit for the flexible transformer were not meant for today, was mainly meant for future grid. So while they were planning to absorb more renewable energy, they wanted to have a mean to be either able to control power flow, but at the same time manage grid strength while the grid is evolving, retiring more conventional generation and putting more renewable resources like solar and battery system.
Do you know if there are other advanced flexible transformers that have been installed elsewhere?
So we are in conversation with several utilities in the US that I'm not supposed to share the name yet, but there are a lot of consideration with a couple of utilities, including one around the South and one somewhere in upstate New York for deployment. But as we know, our industry is a very, very conservative industry. So every new technology needs to really go, I would guess, slowly for acceptances. But we are getting reached out by several utilities, including even outside. I actually have a presentation planned for Seagray where some utility were interested to reach out after and discuss more in detail. But as of now, the Columbia utility installation is the only physical installation today for the flexible power transformer.
Thank you. Cesar Augusto Rego Velasquez is asking, what's the relative cost compared with a conventional transformer?
That's another good question. So it all depends. The reason why I say it all depends is, as you know, transformer, they are very customized when they're getting installed. The overall cost when we are talking about the transformer without much feature, let's say without tertiary and without some of those additional maybe things, can be anywhere between 15 to 20% of the cost. But when you start to add those additional features that I mentioned, so it can go up. Obviously, also this cost was based more on auto transformer application. When we are talking about two winding transformer, which are a little bit more complex than auto transformer, the cost can be also looked at around maybe an additional 50% more. But the benefit in those cases, again, depends on what's the overall application. As I mentioned, this cost figure that I give are based on a comprehensive flexible transformer, which also include three low voltage rating, which allow the transformer to be at the same time a universal spare. The costs go significantly down when it is targeted for just one point-to-point application.
Okay, thank you so much, Ibrahima. We're going to move to our next speaker, who's Amelia Chokiewicz from UC Berkeley, and she's going to talk to us about advanced conductors.
Hi, everyone. My name is Amelia Chokiewicz. Thank you for the introduction, Melinda, and thank you for having me and to the entire organizing team. I'm very excited to be here to present our work on advanced conductors on behalf of myself and my colleagues at UC Berkeley and Grid Lab. So let's kick things off. What is an advanced conductor? So basically, most of the US power grid and power grids around the world have been wired with a century-old conductor, which is called aluminum conductor steel reinforced, or ACSR. And basically what an advanced conductor does is it swaps out that conventional steel core for a composite-based core. So on the left, you see that traditional conductor, and on the right, you see that advanced conductor with the composite core and also trapezoidal rather than circular strands. These conductors are also known as high temperature, low sag conductors in many places of the world. And basically what that composite core allows is that the conductor can operate at higher operating temperatures and fit more aluminum, basically to achieve around a 2 times increase in opacity. These advanced conductors have so far mostly been used in reconductoring projects, which basically replace a transmission line's existing conductors with these advanced conductors with an existing right-of-way and utilizing existing towers and basically upgrading terminal equipment as is needed. What is really advantageous about reconductoring is that it's significantly faster than building greenfield transmission, at least in the US and Europe and many parts of the world. New lines these days are often taking 10 to 15 years to be built, if they are even built. And so the benefit of reconductoring is because the permitting process is significantly reduced. These projects are typically deployed within a period of several months to a few years. Now, compared to some of the other grid enhancing technologies and advanced transmission technologies that we have seen, reconductoring offers a structural increase because it's permanent. And it's quite significant, about 2 times on average. But there's, of course, different addings and different technical characteristics that can provide a larger capacity increase as well. And in terms of just the most viable opportunities, reconductoring projects can be basically performed across the larger power system. So there's significant opportunity for them as well. However, what me and my colleagues saw was that there has been a very slow uptake of advanced conductors in the US. But on the flip side, countries like Belgium and the Netherlands are actually reconducting their entire high voltage networks by the mid-2030s, basically to integrate more renewables, manage congestion, accommodate basically electrification and many other reasons. And for them, this was just the most cost-effective and rapid opportunity. I will note that advanced conductors can also be utilized in greenfield transmission. The key advantage there is that they often carry about 30% lower losses than an equivalent diameter ACSR for the equivalent line loading. So they're also definitely being deployed in greenfield projects. But again, the real benefit is utilizing them in reconductoring projects, again, because of that speed advantage. So if we go to the next slide, basically our first step in this work was to analyze the capacity increase possible in reconductoring. So in this first figure, we derived the St. Clair's curves, which are basically a piecewise function showing line loadability as a function of line length. The capacity increase obtained through reconductoring usually depends on the line's limiting factor, which is generally a function of the line length. So short transmission lines are generally limited by thermal limits, while long lines are constrained usually by voltage or stability limits. So what we found is that 98% of existing transmission lines are actually short, under 50 miles, and basically reconductoring with potentially additional reactive compensation, such as voltage support, essentially doubles the thermal limit of the line. What our next step was to look at costs of reconductoring. So we first began by deriving bottom-up cost estimates. So what a lot of times people say is that reconductoring projects aren't incentivized because the advanced conductors tend to be 2 to 4 times more expensive on a unit length basis than traditional conductors. However, if we compare this with the proper counterfactual, which is if you want to increase capacity through a given corridor, you really have 2 options. You can reconductor it with an advanced conductor, or you can build a new parallel line next to it. So if we compare it with reconductoring projects with building a new line, we find that they're 1/3 to 1/4 of the cost of a new build projects across all voltage levels. And this is just coming from bottom-up cost estimates. Then when we looked at empirical data, so from the Netherlands and Belgium, which are deploying advanced conductors at scale, as well as a few jurisdictions in the US, such as CAISO, MISO, and ERCOT, which have done some limited reconductoring projects as well. Again, reconductoring projects clock out to be less than half the cost of new build projects on $1 million per mile basis. So for us, it seemed like reconductoring was a really great untapped opportunity. So what we wanted to do in our research was to implement reconductoring in a capacity expansion model. So on the next slide, you'll see our work. We began by taking the REEDS model, which is a system capacity expansion model developed by NREL. It's a synthetic network of the US composed of about 100 nodes connected by 300 transmission paths. And we basically plugged in reconductoring into the model and investigated 4 scenarios. So with and without reconductoring, and with and without restrictions on the build-out rate. So what are these build-out rate restrictions? Basically, we wanted to simulate the permitting challenges and cost allocation challenges that are plaguing the build-out of greenfield transmission lines in the modeling. So those restricted build-out rates basically mimic the rate of historical transmission expansion in the US over the past decade. So what we found in our modeling is that basically because of these restrictions on new greenfield transmission, just allowing reconductoring in the model enables up to 4 times the interzonal transmission capacity increase to be added at a similar cost by 2035, resulting in an over 90% clean energy system. So that restricted build-out case is really, you can call it the business as usual case. because more likely than not, we're still going to be faced with significant permitting challenges, despite a lot of progress on that in recent months. Reconductoring is still a much faster opportunity. So if we hone in on the figure in the bottom left, you can see that in that restricted build-out case, by 2035, reconductoring accounts for about 90% of the added transmission capacity, with 10% being composed of just new traditional greenfield transmission. So what this means is that if we go all in on reconductoring and we seriously considering reconductoring as a transmission capacity expansion option, it can actually fulfill most of our transmission needs in the near term, which is good news because, again, like I mentioned earlier, new transmission lines can take 10 to 15 years to build. And if we're talking about meeting certain climate goals by 2035, that obviously would be a risk. So basically, the larger and broader transmission capacity increase allowed by reconductoring accesses lower cost and higher quality renewables around the country. And this translates into quite significant system cost savings. So about $85 billion US by 2035 and $180 billion by 2050. All our results are available in an interactive dashboard. So you can basically kind of see those indicative corridors where it might make sense to reconductor. An interesting thing that we found in our modeling is that reconductoring really supports the build out of wind because it helps to increase transmission capacity on those key corridors, taking wind resources from the Midwest and the central US into load centers on the coasts. So I'll wrap it up there. I encourage you to check out our report for further work. And if you have any questions or want to stay in touch, my email address is up on the slide as well. And I'm looking forward to questions.
Great. Thank you so much, Emilia. Great presentation. While the audience is coming up with questions, I'll ask you a few. Where do you, are there places in which you think advanced conductoring would not be a great first choice?
Yeah, a very broad question. I think what we're trying to argue is that advanced conductors should be considered and reconductoring should be considered at all, because that's not in the discussion in many transmission planning circles today. There's been some good progress on that, I think, with FERC Order 1920. But we are just trying to advocate for the consideration, and not consideration in terms of a band-aid solution on one particular line, but again, for the system-wide scale. So maybe one positive example from CAISO. So we are based in California, and we did a lot of outreach with California stakeholders. And in their latest transmission plan, they actually took us up on some of our insights, and they're proposing reconductoring, I think, about 9 transmission lines leading right into the Bay Area. So this is, for example, I think a great use case for a first reconductoring project is really bringing power into densely populated load areas that are facing rising rates of electrification. And so maybe this wasn't a great answer to your question, but I tried to flip it around and show where is a very good first case for advanced conductors.
Yeah, because boy, San Francisco is incredibly crowded. Trying to get a new right-of-way there would be a Herculean challenge, I'm imagining. And with electrification of buildings and vehicles there, yeah, I'm sure increased capacity on transmission lines is very much in demand. There is a question here that says, thank you for your presentation. Is the interactive dashboard accessible online?
Yes, of course. So if you go to the 2035 report website, on the reconductoring tab, the interactive dashboard is available. It's linked there. So definitely encourage you to check it out.
If other people have questions about reconductoring, this is a good time to ask them. Don't be shy.
Yeah, I do see one in the chat about doing an energized cable replacement and coordinating outages. This is a very common question that we get as well. The good news is that there have actually been examples of live or energized reconductoring. So for example, at the time that it was completed, this reconductoring project in Texas in ERCOT in 2016, it was actually the largest reconductoring project ever. So it consisted of over 200 miles of 345 kV line that was reconductored with an ACCC conductor. And they did it entirely live. So basically putting up temporary poles within the existing right-of-way, never taking the line out of service because they could not afford to, I guess, cut off essentially part of the grid. And it was successful. It was actually completed millions of dollars under budget and much faster than expected as well. There's also a lot of examples in India, which I didn't mention. India has been a huge adopter of advanced conductors for similar reasons in terms of needing to accommodate rapid rise of electricity demand. And they also oftentimes do reconductoring projects live. So there's a lot of examples in terms of how the costs pan out. When we looked into the ERCOT case, it didn't seem particularly more expensive. But my understanding is that is a safety concern just with handling conductors at such high voltages. So maybe to sum it up, not ideal, but technically possible.
Okay, a lot of questions have come in the last few moments. Even Santana asks, do you have any insights on current manufacturing capacity for these types of conductors? Are there any big players already, or is it still being built out?
Yeah, so the good news is that, well, we're discussing it as if it was a new technology, but many of these advanced conductors have actually been in production for about 2 decades. So you have big players like CTC Global, 3M, Southwire, Epsilon, TS Conductor as well, with quite ample manufacturing capacity just from some of our preliminary estimates. A lot of that manufacturing capacity is based in the US, actually in California, at least CTC Global and TS Conductor, which was ironic, why is the uptake of advanced conductors not higher in California? A lot of that is going for export. But I think the tides are changing now. And I think there's also just been so much global deployment, like I mentioned, Belgium and the Netherlands, India, China, in South America, CTC Global has a production facility. So it's definitely, I think, a global movement at this point.
Here's a question from Pomoza Mativa. Could you explain how the integrity of high temperature, low sag HTLS conductors will be tested and monitored over several years following their installation?
Yeah, so the advanced conductors or HTLS conductors have undergone quite stringent and rigorous industry testing by all sorts of accredited organizations, SIGRE, IEEE. They've gone through that robust testing, and I think we have to move past kind of the stage of demo projects now. I think now is the time to deploy at scale, if that makes sense. They've been tested and proved over time.
Here's a question from Philippe Gonzalez. You mentioned a reduction in losses allowed by advanced conductors. Why is that, since it seems they have the same cross-section area?
Yeah, so exactly. We were talking just about reconductoring with a equivalent diameter conductor. Of course, you could swap it out, for example, for an equivalent weight conductor for a higher capacity increase. But in terms of the loss reduction, if we think about simple math, losses are I squared R. Advanced conductors have a lower R, a lower resistance. because of the fact that they use more annealed aluminum and they have a composite rather than a steel core, and can operate at higher temperatures. And so that's really where that loss reduction comes from. It's just a lower R. But I want to caveat that, of course, if you're doing a reconductoring project and you want to get that higher ampacity and that higher I, you're just by nature of math, again, your losses are going to increase because of I squared R. If you're increasing I, your losses will increase as well. So that loss reduction really has to be compared to a traditional ACSR line at the same line loading.
Here's a question. Reconductoring is only one item to increase capacity, but what about the next limiting component, breaker, substation? It won't truly increase capacity. How is that taken into account in your study?
Yeah, I appreciate this question because I neglected to mention in my presentation. So it's definitely true that if you increase the ampacity of the wires, chances are you probably have to increase your transformer equipment or protection equipment at the substations to accommodate those larger power flows. So what we did in our study is we just conservatively assumed that every conductoring project will require a brand new substation, and we factored in those costs. Of course, this is probably unlikely. Of course, you might have some land constraints or the like, but you probably won't have to require a brand new substation. But we wanted to make sure we were making a conservative assumption and accounting for those costs in our modeling. So this is also kind of where we want to pass the baton on to ISOs, RTOs, utilities to conduct their own studies. Even though we can estimate, for example, the rating of a power line based on its voltage level and length, we can't estimate the rating of their terminal equipment. That's information that the utility knows. So that is just one limitation of our study and why future work in this area is important.
Thank you. And Patrick Brown would like to know, how do you account for the terrain-dependent costs for reconductoring, such as going through urban or wetland or mountain areas?
Yeah, at least in this study, we didn't explicitly account for terrain-dependent costs. Also an area of future work as well, definitely. Of course, definitely for reconductoring projects, costs associated with installation and terrain will be lower than greenfield transmission projects.
Okay, great. I think we need to move on to our final speaker. Thank you very much, Amelia. There might be one or two questions that we didn't get a chance to. If you could write an answer, that would be great. Our next and final speaker is Leonardo Reese at ONG, and he is going to talk to us about point-to-point HVDC.
Linda, thank you. So let's move to the next slide. So we are entering a different topic in terms of advanced transmission solution here. So we've got to know a lot of options to increase transmission capacity, transmission flexibility through software, through hardware, through better management of the grid. Now we'll look at another harder option. And before going into technology, I said, why not starting with why this is relevant? So just as an example, this is Europe's view, or part of Europe's view, for HVDC transmission technology and its role in today's and future electricity grid in Europe. So looking at ENTSO-E's 10-year network development plan, we see that about 59 to 60% of proposed new transmission investments are in HVDC links. HVDC links to do what? To do a variety of different functions along with moving power around the grid. To a large extent, bringing offshore wind from the North Sea to the continental Europe, So we see that Europe has planned to deploy 65 gigawatts of offshore wind by 2030 and 150 gigawatts of offshore wind by 2050. And the more offshore wind we deploy, the further we are from the continent to the continent. So we need to increase our transmission distance, and we will see later that by doing that, going with high voltage AC becomes challenging technically and from a cost perspective as well. So HVDC is the natural choice for that. So the more offshore wind we deploy in Europe, the more HVDC will be associated with that to bring all that HVDC to the load centers onshore. But it's not only that Europe is planning for HVDC. They also are planning to increase transmission capacity between countries. So increase power exchange between countries to benefit from a very diverse portfolio of generation and load resources all across Europe. And also, we will have other projects, HVDC projects within countries. So within the same country, we also have several HVDC projects being proposed. If you look, for example, for the case of Terna, the transmission system operator in Italy, they recently published their hypergrid project development plan that is basically a big transformation of their transmission grid by intensive use of HVDC technology. New HVDC technology onshore, offshore, and also conversion of existing HVAC infrastructure into HVDC. So if we look to another example in Europe, we can look at TenneT, so transmission system operator in the Netherlands and part of Germany. They developed what they call the 2 gigawatt program that is basically a standardized HVDC solution for the connection of offshore wind to Germany and the Netherlands. Just as an order of magnitude to see how much money is around the table and how many investment we see in HVDC in Europe these days, just between 2022 and 2023, TenneT awarded more than 10 billion euro contracts to develop HVDC transmission assets to connect different offshore wind plants to the onshore grid. Next slide. So as I mentioned, so Europe deploying a lot of HVDC, not only Europe, we are seeing this trend a bit all around the world. So why so much interest in this technology? It is because it's a technology that can offer transmission service in a wide range of different applications. So a very classic application of HVDC, and most probably one of the first applications of HVDC, is long distance transmission. More cost effective, technically performant than HVAC over long distances. The second one is longer submarine underground cable application. Whenever you deploy cables longer than 40, 50 kilometers, deploying those cables in AC starts becoming technically challenging to manage reactive power production of those cables, and also quite costly due to all the additional compensation you need to bring with. So if you need to deploy long distance submarine or underground cables, HVDC is usually the technology of choice. Another very classical problem of HVDC is connecting asynchronous grids or asynchronous areas in the same grid with the same frequency or even with different frequencies. So we use HVDC that is capable of completely decoupling the AC nature of the grid and putting those grids together. We can also do power flow control through HVDC. And in those cases, most of the time, what we have is what we call embedded HVDC. So when we have an HVDC connected in parallel with the AC network, and then by using the controllability of the HVDC link, we can control flows through the DC links themselves and across the AC network. Another very classic example of HVDC application is connection of remote generation hubs. Historically, we did a lot of that to connect big hydro plants very far from demand centers to demand centers. These days, we are seeing a lot of projects being proposed to connect wind or solar generation hubs to main load centers through HVDC. And then something that can come as a byproduct of the HVDC together with the transmission capacity is the ability of ancillary services provision. Reserve sharing, voltage control, power oscillation damping, grid forming, black starting, and many others. Basically, whatever an inverter can do in terms of ancillary or grid service provision, we can do that with HVDC as well. Next slide. So I took two examples of HVDC projects in Europe just to give an idea on different applications. So the first one that I chose is working on converting existing HVAC infrastructure to HVDC to increase transmission capacity on a same right-of-way. So Germany is developing a project called Ultranet project that will, when completed, be running north-south across Germany, connecting the wind hubs in the north of Germany to the main load centers in the south of Germany, and resolving, hopefully, the historical north-south power flow constraint in the German grid. So that project is a VSC HVDC technology 400 kV that was used to convert. So the line is an existing AC line, double circuit AC line, where one of the AC circuits is now being converted to DC to run that DC line. And that DC line then will have a 2,000 megawatt capacity. So no new right-of-way, just repurposing an existing double circuit AC line now being a mixed HVAC, HVDC line, same right-of-way. As you all may know, Europe, it is very challenging to build new rights-of-way. So anything we can do to increase transmission capacity without new rights-of-way is very welcome. And this is a very interesting application of HVDC to increase grid capacity using same rights-of-way. Next slide. The next slide is the about the Aachen-Liège electricity grid overlay, the Allegro HVDC link between Belgium and Germany. And this is a link, 1,000 megawatt, 90 kilometers VSC HVDC link between Germany and Belgium. And this one, other than increasing power transfer capacity between Germany and Belgium, it also helps to achieve better controllability of the power flows in Germany. Because remember, I mentioned from the previous slide, in Germany, we have a very hard transmission constraint between the north and the south of Germany. And that constraint even impacts the operation of the transmission grids in the Netherlands and Belgium due to loop flows. So when you have a lot of wind power coming in the northern of Germany, you have the congestions in the Dutch and Belgian grids, limiting the transfer of wind from the north of Germany to the south of Germany due to this loop flow. The Allegro HVDC link, one of the greatest impact it has in the grid is to improve power flow controllability in the area between North and South Germany. So by controlling this loop flow across the Netherlands and Belgium. So this, again, it increased power exchange between Belgium and the Netherlands, but also as another consequence of this link is that you can better manage the loop flows between Germany and the Netherlands and Belgium. You have also other grid services being provided by this DC link: reserve sharing, voltage control, power oscillation control, grid forming capability, and black start capability. So this is an HVDC link with grid forming capability. That is, let's say, a keyword of the moment in grid forming. This is a real example of a real HVDC link, 1000 megawatt with grid forming capability. Next slide. So everything that I mentioned before is point-to-point HVDC. But remember that I said Europe is looking by 2050 to deploying up to 150 gigawatt of offshore wind in the North Sea. That in the baseline scenario, most optimistic scenarios are considering more than 200 gigawatt of offshore wind deployment in the North Sea by 2050. So the next frontier here is, how do we go from point-to-point HVDC towards multi-terminal or meshed HVDC grids? So there's a lot of work ongoing in Europe and other countries around the world trying to define or understand how can we go from historically point-to-point HVDC link toward multi-terminal or meshed networks on the DC side to increase reliability, improve grid flexibility, and combine system interconnection capabilities with offshore wind integration. So that doesn't come free of challenges. So there are many different challenges. I'm listing 3, but I could have listed 10, 20, 30 different challenges. There are many. So one of them is an interoperability. So in this case, you will need to put together equipment manufactured by different vendors. And it is not like in the AC grid where the integration of these different equipment is naturally done through physics. In the DC side, this integration is done through control and communications. So you need to define your interoperability rules very clearly so that equipment manufactured by different vendors, they can talk together and work together smoothly. The other challenge, very well known for multi-terminal mesh DC grids, is DC fault protection. We cannot use circuit breakers like in the AC world. For DC fault protection, we need special DC circuit breakers, another very active area of research and development these days. And linked to interoperability, we have standardization. We need standardization in functional specification. We need standardization in design of equipment. We need standardization on operation practices, and you name it, a lot of standardization is required. If we go to the next slide, and this is my last slide. So a lot of challenges, as I've just said, how Europe addresses all those different challenges. Very first one, through research, development, and innovation. A lot of EU-funded R&D projects currently ongoing. Promotion that finished a few years ago on meshed multi-terminal HVDC for offshore wind integration. HVDC-wise, looking right now how HVDC grids could improve grid resilience and reliability. Intropera, that is an R&D project looking into interoperability of HVDC grids. The 20s R&D project, and you name it. There are many currently and recently concluded R&D projects on R&D. And HVDC has been added as a strategic technology in the European Energy Transition Plan. So that sets R&D priorities all across Europe. So very important topic from R&D. On the other side of things, network codes. And so I think 8 years ago, they published a dedicated grid code just for HVDC. And so there is the 2015 version of that, update on that under consideration. So already there is a grid code framework for HVDC. Standardization. 10net 2 gigawatt program is one very clear example of standardizing design and deployment of HVDC. Intrapera, the R&D project, trying to define what are the rules needed for interoperability. We have a Senelec HVDC grid system standards that was published not long ago. We have ENTSO-E working groups actively working on offshore wind and related HVDC applications. And together with all these, there is policy looking into providing incentives and support mechanisms for the deployment of all these HVDC grids. So a lot of the HVDC grids that I showed in my first slide, they are now considered as projects of common or mutual interest, and they benefit from accelerated permitting process and funding from the European Commission. So a lot of work going on HVDC, a lot of interest in HVDC. It is a quite old technology, but since it was first deployed, it has evolved a lot and continue to evolve until today, and will continue to evolve a lot and very fast in the next few years. And with that, I stop here and take any questions that you may have.
Thank you so much, Leonardo. Before you got to your slide where you mentioned multi-terminal HVDC, Fernando Palma asked, are there any multi-terminal HVD deployments, and what's the limiting factor of deploying more of that type of HVDC setup?
Yes, we have some examples of multi-terminal HVDC projects. So we have one quite old between the US and Canada that is a multi-terminal HVDC using line commutative converter technology, operating for many decades already. So one example, China has a few of them in LCC mostly, and you have one hybrid multi-terminal HVDC link in China that is LCC link with one VSC terminal. You have also in China under development one concept of meshed HVDC with VSC and LCC. You have the project that I presented for Germany, so the Ultranet project. That project is point-to-point in the first phase, multi-terminal ready for the second part of the link that goes up north, the extreme north of Germany. There will be a second HVDC that will connect, so we will have 3 terminals forming a multi-terminal link. What are the challenges? Very first one is DC fault current handling. So we need, with multi-terminal, if we are working only with 3 terminals, we can still discuss the need or not for the DC breaker. There might be ways of having solutions with full bridge converters and avoiding the DC breaker. But going further than that, DC breaker is a challenge. Technology is still under development, even if we have a few DC breakers already entering the market, but we are still in early stages of that. The second challenge to that, just to name 2, is very difficult that you deploy a multi-terminal HVDC project all at once. So normally those things should come together over time. So it is very difficult to take an existing point-to-point link designed to be point-to-point and extend it to multi-terminal. Either you design it as multi-terminal ready from the beginning, otherwise it will be very costly to extend that towards multi-terminal. And then you have everything that I've just mentioned on interoperability, for example, that is challenging. It doesn't mean that it is not possible to do it. We have real projects, but it is technically and from a cost perspective also quite challenging.
Leonardo, we have several more questions from Arturo Alarcon and Barbara O'Neill, who says we miss you. If you could please write answers, that would be great, because our time is up. And I want to thank each of our 8 presenters. I want to thank Sophie Schrader, and I want to thank our sponsors, RELAC and Inter-American Development Bank, and our interpreters. And please do fill out the survey, which you will receive in just a moment. Thank you, everybody, for your participation, and I hope you learned a lot. I know I did. Thanks, everybody.
Thank you.
Bye-bye.
Thank you so much.